good afternoon. So, I'm from. Have to press something. Okay. So specifically, I'm from the Humanoid Sensing and Perception group within the Italian Institute of Technology, which is one of the groups that in the past years contributed to the development of ergoCub, one of the humanoids, let's say. Now there are so many. And it's in Genoa, so nice weather. And in this seminar, we will talk about tactile perception and manipulation, and specifically how to develop a tactile model of a fingertip that is aimed to bridge the gap between simulation and reality. And then we will see how this tactile model can be useful to learn tactile motor policies in simulation. So recent deep learning models are transforming robot perception and manipulation by combining different input modalities: vision, proprioception, language, and even touch, and whatever sensor you can use is better to use it. And touch is still unsolved, let's say. It's a very active research area, and it's very useful, especially when vision is occluded or is disturbed. For example, vision models, when lighting condition change, might go out of distribution, and you might have a degradation in performance. There are two main paradigms of robot learning: imitation learning and reinforcement learning. In imitation learning, the robot learns from demonstrations of the task, while in reinforcement learning, the robot learns from experience by trial and error. Typically, with imitation learning, you collect the demonstrations with tail operations, and with 10 to 50 demonstrations, you can have a good performance. The downside is that collecting demonstrations can be expensive and time-consuming. With reinforcement learning, however, the robot can interact with the environment, and it can potentially discover more optimal actions and have a better performance with respect to the demonstrations, but it's very time-consuming, and usually training is performed in simulation and then transferred to the real world. In this setting specifically, it's important to simulate your tactile sensors. And in fact, in this talk, first we will see how to simulate a tactile fingertip of the ergoCub, and then how to use it to learn grasping policies in simulation with reinforcement learning. We use ergoCub at the IIT, which is the evolution of ergoCub, and this one is aimed for industrial manufacturing scenarios. The hands of the ergoCub are equipped with tactile fingertips, and these are developed by an external company in collaboration with IIT. And each fingertip has 5 tactiles, which are all effect sensor that measures the 3 axis change in the magnetic field, and the tactiles are covered by a magnetic skin that deforms when there is contact. So 5 tactiles, 3 axes per tactile, so in total each fingertip gives us a 15-dimensional signal. To model the tactile fingertip, first we collect data from the real world. So we have the experimental setup comprises a tactile fingertip fixed on a bench, and there is a robotic arm and a force sensor with a spherical indenter, and we move the indenter to touch the surface of the fingertip. And we can collect a data set comprising reference indenter position, force, and taxels. And this is how we can visualize the taxel activations. So we 5 taxels, each one has a time series of 3, and then the contact forces. So now it's a good time to stop if you have some doubts. Yes.
Is there a calibration process with the sensor? How do you ensure it's accurate?
How do we ensure it's accurate? So, what do you mean? I mean,
Do you have to calibrate the sensor?
sorry?
Do you have to calibrate the tactile sensor?
Well, it's already calibrated. At the beginning of the tactile data collection, we just collect the rest values, so that at the end we have the reference 0, let's say. But yeah, this is the only calibration we do.
And is there any hysteresis in
Yes, there is.
but is that usually known by the manufacturer, or do you have to figure it out yourself?
We have to figure it out, yeah. And yeah. So one question I can give it to you is why do we need both taxels and contact forces? Can't we just have the taxels or just the forces? Well, if you see the drawing, the taxels don't cover all the surface. So there might be a contact point where the density of the taxel is low. And so you don't get the taxel displacement, even though there is a force. And in fact, as you see, I have to use this because my girlfriend gave it to me, the laser. If you see this area, you have non-negligible forces, but most of the taxels have almost 0 activation. This looks a lot, but is a low scale with respect to the others. So having forces together with the taxels is useful.
So the force, it's the force that, so the last plot,
Yes.
is the force that you collect from the measuring setup? Or
Yes. Yeah.
additional sensor?
From the setup.
Okay.
So it's the force because there is a tactile sensor on the robotic arm before the indenter.
Okay. So how do you, can you show the setup again?
Yes.
Okay, so you have a force sensor, is like,
Force sensor is this.
okay.
So if you touch, for example, this part, there are low. The taxels might not measure it accurately, but you still have a good signal from the force. Yes.
Regarding this setup, why are we picking a sphere? Because I would imagine that the data set might then be a bit biased towards like spherical objects, for example. Is it because it's quite general for downstream tasks?
Well, there are a few reasons. One is that you don't want to ruin the fingertip. And actually this was a square. So generally you collect data with many shapes of the indenter. In this case, we have a sphere. So now that we have the data set, we have to use it to develop an accurate simulation. So our framework comprises the following. We have a physics-based simulator, for example, MuJoCo, Isaac Sim, from which we can extract information about the contact and the sensor. Then we can construct our own tactile features, we will see later, still in simulation. And then we have a neural network to predict the tactile observation, the real tactile observation. So maps simulation to real. We will see that we deploy it with 5 to 10 fingertips, and the neural network is a transformer encoder that processes the tactile features, and then there are specialized heads to predict the taxels and the force. So this is an example of a simulated tactile data collection. So the first step we do is to recreate the simulated, the real tactile data collection in simulation. And from here we can extract a simulated data set. We know the indenter position, the contact force, and many other things, but not the taxels. So generally, MuJoCo offers many things, but to simulate the magnetic taxels, it's a bit difficult. How do we make sure our simulated tactile data collection replicates the real data collection? We define an optimization problem where we minimize 2 objectives. One is the indenter position error, because we want the simulated indenter to track the same trajectory of the real indenter. And one is the force, the contact force error. We want the simulated forces to be as close as possible to the real forces. To do this, we define some parameters that we want to optimize. For example, the actuator position gain and velocity, and we define some constraints. And the fingertip, for example, the stiffness, damping, and friction of the shell. We perform a Bayesian optimization, and we get some results. These are the results that minimize the objective functions, the parameters that minimize the objective function. And how does this simulation perform? Well, we can see the box here, and you have sub-millimeter position error and some force error. These are the percentages with respect to the scale. And well, is it good? We compare it with 2 baselines. One is the naive simulation, where you put most of the, well, you put those 5 parameters to default. I mean, imagine you don't have any simulation knowledge, you set it as default. Of course, it's a very bad simulation. And of course, usually you do manual tuning, but it's time consuming. And another baseline is a random baseline, where we sample from a distribution of simulations. So from those parameter ranges, we sample several sets of parameters, we evaluate them, and we get the results. So as you can see, getting a low error on position is fairly easy by random guessing, but getting a low error on force is more difficult. And then we can evaluate the time series of the simulated, the optimized simulation and the baselines. And it's useful to visualize a contact and non-contact point. So, questions? Okay.
Can you put back a couple of slides? One more. Yes. So, so the identer position error. So these errors, like identer position and contact force, will be the difference between what you measure in simulation and what you have in the real setup.
Yes.
So they are not independent with each other, like, or are they? Like, if you
They are coupled, let's say.
They are
A bit, I mean, yeah.
because
If you get the position wrong, you will not get a good force,
Yeah.
probably.
yeah, right.
Mhm.
Okay.
Yeah, the only trick is that on the dataset, we don't have the real indenter position. We have the reference position. So when the robot touches the fingertip, it doesn't actually go to the reference. It stops a bit earlier.
And also maybe you probably also have some deformation.
Yes.
That you don't.
Yeah, and so we don't want to get zero position error.
Yeah, yeah. Yeah, kind of bounded. Okay. And then, and the simulator parameters, so it's actuator. So what is the actuator in simulation?
Well, instead of simulating the robotic arm,
Yes.
we have 3 virtual position actuators that move the sphere.
So why don't you just set the position of the sphere in the?
Because we want the wall dynamics.
Okay. So you want to reproduce actually the pressing.
Yes,
Okay. So it's not just the position. Okay.
but probably if you just set the reference position, maybe you get good results as well.
And the other ones, the other 3 parameters, which are the stiffness. Okay, so this will be the soft. This will be actually the soft material, kind of trying to
Yes.
estimate the material properties of the real.
Yes, yeah, Imujoko doesn't give you so many options, but these are the
Okay.
common parameters, let's say.
Stiffness, damping, and shear friction. And you have this range of parameters. So for each parameter, you have some range. Is that kind of a bit random, or you have some idea?
Well,
Correct one?
we tried
Okay.
to select reasonable bounds.
Okay. And so in Mujoko, so you're using Mujoko for that simulation, right? So
Yes, I mean it's general, but we are using Mojoko, yes.
Yeah, yeah. Can you show previous slide? One more.
This one.
Yes.
So we are still here. We are optimizing this part.
Okay. Okay.
So after we have optimized the simulation, we trust it, and we can generate simulated data. So once we run the simulation, we extract information and construct some features. Here we constructed a vector of 37 features, 3 for the contact position, 3 for the contact normal. 1 that you can only get in simulation is the simulated the contact penetration, because usually in simulation 2 bodies in contact penetrate slightly. And then we have the distance between the contact point and each taxel. And we also have the alignment between the contact normal and each taxel reference frame, because if you see, for example, this taxel has another orientation with respect to these others. And now we are here. We can construct tactile features in simulation, and now we want to train this neural network to predict the real taxel and the real forces. We run a training, and if we visualize the losses for taxels and for force in train and validation set, we have these results. We can see that training forces is slightly more difficult than training taxels. Yeah, 1 second, we have some delays. Okay, and this is at inference. The neural network at inference to predict the taxels. So this is the mean of the 5 taxels, and these are the force error. As usual, we see time with contact and no contact, and we have a very good performance, let's say, in this setting. One thing we asked is that is training on taxels and forces helping, or is it better to have one model for the taxels and one model for the forces? We saw. Are you familiar with freezing the neural network? Okay, so we evaluate 3 models. One where we train both the taxel end and the force head. One where we freeze one of the other, and one where we freeze the other one. The multitask learning is the purple one. Taxel only is the green, force is the orange, and we see that generally training on both taxels together helps. It's not dramatic, but it always helps. In particular for learning taxels, the benefit is higher. So, questions?
Sorry, when you say taxel, you mean the output of
The output, yes.
the magnetic fields, basically. So
Yes.
the output of each taxel.
Yes.
And force would be the 3D force.
Yes.
What was the reasoning for choosing transformer model architecture? Just the encoder part specifically.
Because, well, yeah. I didn't say it, but from the tactile features, as input we actually take a window of past observations. So we have a sequence. So to process sequences, transformers are one of the state-of-the-art models. And just the encoder, because I just want a common representation. So I don't want to generate new data. I want to just encode what's in this sequence. Okay.
So, can you go back to the previous slide?
The previous.
No. Aspetta, wait. Panico.
No, previous. Yeah, this one. So okay, so you okay. How do we? So you align. So you have the simulation data and the real data, and you align them by the position of the indenter.
Yeah, we have.
Yeah. So you have for the same position.
We have.
In the enter,
Yeah.
you have
Yeah, we have time steps. We align the time steps.
so you okay. So yeah, you actually reproduce the same sequence.
Yes. Yes. And yeah. So. Yes.
What is the reason for why the validation loss is lower than the training losses? With dropout units in the training?
Yes. Yes. But the reason is so low compared to the training set. It depends what you do during the training. So you can do many ways. So usually you do mini batch updates. So if you plot for each epoch and you average those training errors, and then at the end of the epoch you validate the model, you are comparing the best model so far, let's say, with all those errors that are from different versions of the model. So in this case, this is why the validation error seems below. But at least when you do this stuff, you care that the validation error does not go up. You don't. It's important, the gap, but the most important is that you monitor the trend. And why does training with only forces is very comparable to training with Tactile and forces, and training with only Tactiles is, let's say, more is worse than training jointly.
So you see, you always see advantage in the multitasking, but you see more advantage when you add force rather than adding taxes.
Yes. Any guess? Well, as we said before,
Because force you always get some.
you always get some force, but the Tactiles are distributed, they are more discretized in the surface. I mean, it can be. So, okay, now we have this tactile model. We put it in 2 environments, and we do some reinforcement learning very quickly. So, the task is to grasp some object, and we have 2 environments. One is a robot hand and a wrist, so we control 9 degrees of freedom, and the other one we control the upper body of the ergoCub, and the core is fixed. We have, as a general overview, a policy that has to map observations to actions, and in our case the observations are proprioceptions and tactile. So the fingertip readings, both with 5 or 10 fingertips, and the number of joints. And the actions are the reference joint position, actually the delta joint position. With the same settings, we train the two policies. We can monitor, for example, the return, just an example, and we can see how they behave. So it's a simple case, but they don't have, these two settings share the same reward, the same policy structure. It's not, the policy is not is instructed to lift the object, just to grasp it. So in one case it's very trivial, the other case it learns something. Okay, so the seminar is finished. So.
So what is the task in the right one, for example? What is the reward?
Well, the reward in both cases is to minimize. Well, there are different components. One is to minimize the distance between the palm and the object and the fingertip and the object. So it works for both cases. You just have two palms in one case, and then we reward some penetration of the fingertip. So to squeeze a bit the object.
So the task is basically to touch the
object. To touch the object, yes. Yeah, we penalize object velocity, so we don't want to slap it or. So let's say it's to grasp it. It didn't learn to grasp because maybe you put some term to.
So ideally, in the humanoid, so the best behavior would be to put the hands on the side and just squeeze it?
Yes.
Something like that?
Yes. The goal is to don't make it artificial. Let's say you can put a reference point here and a reference point here.
Of course.
In this case is general, but you don't always get what you want.
Yeah, no, of course. So basically, in the reinforcement learning, you're kind of encouraging to generate the contact interactions.
Yes.
But without moving the object.
Well, object velocity is penalized a bit, so you don't want to move it too much. Of course.
If you penalize it a lot.
If you penalize it a lot, it will be maybe it helps. But later, if you want to lift it, you don't want to keep that penalty, that high penalty.
Yeah.
So for now, it's a bit of penalty, but not so much.
So in the hand one, yes, you just expect the finger to close around the object.
Yes.
And basically the fingertips to touch.
Yes, because we reward it to have some penetration. Otherwise, it would stabilize.
Yes.
more.
So here, so basically here you have the, so you use the tactile fingertips readings. Are those
Are those given by the tactile model we developed?
okay, so it's the kind of real, so it's
Is there,
the
let's see.
simulation of the real readings.
Yes, yes.
But for the simulation, you don't really care, or do you?
We
I mean, if it was only to work in simulation, then
Well, the next part of the work will be to then transfer
right,
in the real world. So in the real world we have tactiles.
yes,
We don't have artificial
yeah.
features, so we want those features.
So, but then the yeah. So this is to prove that even if you use the readings generated by your model, the behaviors that you see in simulation are still reasonable.
Yes, we didn't prove the model is helpful, but we proved, let's say, it can be used. It's a work in progress.
Can you show previous slide?
And these policies are trained from scratch. So it takes a bit of thousands of iterations to see if it's working or not.
So the overall, the generation of the tactile readings, is it time consuming? Is it computationally expensive?
No, it's a compact model. It's very efficient.
And so in the simulation, so the data that you actually gather directly from the simulation, it's the, so you still have like to detect when you have a contact, you use the compenetration, or like.
Well, if there is a contact, you know it. you can read the contact list, but yeah, you can check the penetration, let's say.
No, but so if you go back like one slide,
You want to see the features?
yeah, back. So with your general scheme, the scheme of the.
Yeah. When I put this slide, it freezes.
It's a best slide. So, because of course, in the end, you want to have this, your simulation that detects the contacts, right? So, in order to do that, of course, you can. So, the input to your model. So you have this learning model that generates the more kind of realistic tactile perception. So the output of that model is the tactile readings and the forces, and the input to the model, what that would be.
The tactile, some tactile features that we construct, which are these.
Okay. So you have the contact position. How do you do the contact position?
From Ojoko you get it. From the simulator you get the contact position.
Ah.
It's you read contact dot position, let's say, from the code.
Yeah, but so is that based on the? So in the simulation.
Specifically, the contact position is So the two bodies penetrate.
Yeah.
So the midpoint between the intersection of those points, of those bodies, is the contact position.
Okay. So it's based on the penetration.
Yes.
And the normal as well?
Is the so a contact position as a reference frame, you get the normal.
Okay, so from ergoCub, let's say you get the contact position, the normal, the penetration, the distance between the contact and each of the taxels.
Yes, then these are, let's say, these are Mujoko,
Yeah.
and these are developed.
Okay. So that one contact taxel distance is for each taxel.
Yes, so it's X, Y, Z. We show for each taxel. Yeah, it's a 3D vector for each taxel. Here we show one taxel, and then the other taxel is they are transparent. Otherwise,
And the contact taxel alignment.
it's let's say the alignment between the normal and the reference frame of the taxel.
For each taxel.
For each taxel.
How do you come up with these features? Intuition?
I mean, yes, intuition.
Have you tried to?
Some modeling experience, let's say. Then you develop the intuition.
Is it any of this that is more useful or less useful, or did you try some modulation with this?
Yes, but it takes a lot to run, so we didn't report it. But let's say contact penetration. I mean, I ask you, what do you think is the least or most useful of these blocks of features?
So you're trying to, so with these features basically, and based on your model, so starting from this feature, you try to estimate the readings of each taxel and
The contact
general
force,
and
yes.
general force.
So if we remove selectively this, what will be the most or least impactful of these blocks?
Should we vote?
We can vote. We can create a Google form. Wait. Or you can ask in the. I don't say anything. You ask it, and then I give you the results, and you evaluate.
But then they blame you for the one.
Yeah. No, I mean, I will not mark. I will just. I will give you the results based on.
So
Well, for example.
So the penetration, I mean, I don't know how much the penetration, so what is the range of the penetration in this? Because the penetration should tell you more or less, it's kind of the pressure,
Yes.
but I don't know how much.
I mean, more penetration, maybe more force.
More force. Then contact position, well yeah, I guess contact position is quite useful.
Yes. Yeah, contact position is useful, yes. Let's say if you only train on contact penetration,
Yeah.
I don't find the button.
So contact penetration, it also tells you in which position.
No,
No.
it doesn't tell you the position, so it's not so useful.
Okay.
It can estimate the magnitude, but not the relative displacement of the taxels.
Contact.
If you have contact taxel distance, you almost have also the contact position.
Yes.
If you have the alignment, you almost have the normal. So these are two position-oriented blocks. These are two orientation.
So actually, if you already have the contact position, why do you need the contact tactile distance?
Yes, it's a good question, but I will answer it at some point. My intuition so far is that if you put also, let's say, if you develop a mechanical model, you have contact position, you have the tactile position, and then the model, you do some subtractions and so on. So you need the tactile position.
Yeah.
So instead of giving to the network the tactile positions, which are fixed, for each contact they are always fixed.
Yes.
We give this signal which is more rich.
Okay.
It's redundant, but usefully redundant. And the same with the normal, with the alignment. It means redundant, but it helps. It helps. I tried, it helps. But yes. Yes.
So from what I've understood, you had to model this in simulation to get this set of features which you can't directly measure, right? And then the encoder, the transformer encoder, is mapping these features back into expected observations to then put into the RL side. So when you're transferring this into the real world, how do you get this set of features to put it into the start of that chain?
You will not use them anymore. Because in the real robot, you already have the tactiles.
Right, so this task of developing the encoder is just for simulation fidelity then?
It's just so that you are able to experiment in simulation.
Right, and then you can do like a...
Sim to real.
Yeah, sim to real, transform the policy.
Yes.
Okay, makes sense.
Because you want to train a policy on what you will get in the real world.
Yeah.
If we were able to get all these features in the real world, maybe the neural network was not so useful. Probably you can do it. So, but you have to make so many approximations. I mean, you can do it, probably. Not the contact penetration, but you will need to estimate the contact positions from the tactile reading. So you will need another model. So
Okay, that makes sense. Just drop it.
yeah.
Yeah, that makes sense.
And so, more general question. So, you went through this kind of route of, basically using real-world data to make the simulation more realistic, right?
Yes.
I guess. So people, I don't know if you know, like people that have done this with the vision. Like I mean, typical, like a lot of the, robot simulation, robot learning simulation, etc. A lot of it is it uses vision as the main perceptual modality, and I think many of the simulators are also much more realistic in terms of photorealism. Right? So do people do that in the visual domain to
I don't know.
use the data from a real world to make simulation more photorealistic?
I don't know. I don't know.
Yeah, I don't know.
I mean, because I don't know those models. I mean, I don't know what gives you the photorealistic image. If it's a neural network, then they have already done it because they train the network with real data. So.
And on the other hand, let's say the other, I think, because of course this is very kind of general problem of try to have realistic simulations. And one option is to use some real data and map from your simulation to real data.
A map, okay.
No, I mean, which is what you're doing.
Okay.
So I guess what will be the limitations here? Like, so for example, I mean, you have to collect some real world data on your setup and try to generate as many kind of diverse stimulations, which then you may happen to encounter during the simulation. Otherwise, you may have, so I'm sure also in your model, apart from the average behavior, you may have some situations that are not mapped realistically. Do you have any feeling, any idea about that? So in that sense, what is the current limitation of this model in terms of being realistic? Maybe it's generally realistic, but not all the time, and in some specific cases it fails more.
Well, when you put the data in the loop, so most of the limitations come from the data. So if your data set is rich enough to cover as many scenarios as possible, but you always get the limitation, but it doesn't cover this. Another thing is that we are assuming one contact point. So if you touch the finger in 2 points, it will get one of these. I mean, yeah, you will not get an accurate result. You can, you can still apply it, but you have to work on it a bit more. Another, then.
So you mentioned, for example, the use of different indenters. So in the end, what you have done was to use only the sphere or to use different ones?
Only the sphere for now. But
and
if you
is that a big thing, or because you use only the sphere, but then, for example, when you try it in the simulation, you have the robot picking the interact
which is
with
flat.
the box, which is flat.
Yeah, that is for sure a problem. I mean, you should train this model with different shapes, ideally. You get some benefit with more indenters, but it's time consuming and so on.
Right. Any more questions? No? Okay. If not, thanks.
Thanks.
Thanks a lot.